Hey, welcome back to Feedback Control Systems. This is Module 12.4, Supplemental Frequency Response Topics. In this module, we're going to review static error constants from the frequency response, look at the frequency response for systems with time delay, and then finally, ways to obtain a transfer function experimentally. So this will be important. Let's say you have a black box, if you will, and you designed a system, or you found a system from a legacy product that you have, etc., and you do a frequency magnitude phase response, maybe using a network analyzer, a spectrum analyzer, whatever, and you have some sort of plots. Now, from that, can you use that to derive a transfer function? So instead of having the transfer function deriving the Bode plots, taking that frequency response data and then getting it back to a transfer function, we're going to at least start to show you a methodology of how to do that. Okay, so first we're going to start with our static error constants based on our frequency response. And remember, we had three of them. The first was the position constant, k sub p, and what we see here is it's maybe some gain k, and then we have the product of our zeros divided by the product of our poles as shown here. So let's just assume I have some sort of frequency response as shown here, and this would be a type 0 system where the initial slope, if you will, is 0. Okay, so we start with an initial slope here of 0, and let's say we have solve for the gain here. Let's just say that this right here is 25 dB. Well, we can simply take that expression, 25 dB equals 20 log of kp, and solve for kp. And then what we'll see is that we get our position constant of about 17.78. So actually pretty straightforward for that position constant for a type 0 system. The next is our velocity constant, k sub v. You'll see that as shown there. And this will be, again, a type 1 system where you'll have an initial slope of minus 20 dB per decade. And what happens there, so here's our slope, if you will, and at some initial frequency here, you'll see some starting point which you could calculate based on there. But this will have like an initial slope of minus 20 dB per decade. But if you take that slope and kind of keep going down to where it intersects the frequency axis here, what you'll see that kV is the frequency where that initial slope of minus 20 dB per decade crosses your 0 dB point. So again, this right here would be our 0 dB point. So that frequency where that crosses, that will be your velocity constant. Then finally, for our acceleration constant, again, this will be a type 2 system. The initial slope will be minus 40 dB per decade. So very similar thing. You extend that slope, look for the 0 dB crossing here, and instead of being directly the value like kV, in this case, it'll be the square root of Ka. So you find that frequency, the square root of that frequency will be your acceleration constant. Okay. Next, we're going to look at the frequency response for systems that have time delay associated with them. So first, what we're showing is the magnitude and phase plots as a function of frequency, and we might have this magnitude plot here, and we talked about gain margin. So where is gain margin? Where the original system, so this is the original phase of that system, crosses 180 degrees, and then we have our gain margin as shown there. And then our phase margin here is when we look at the gain plot at 0 dB go down, how much phase do we have until we hit 180 degrees? So that's what we've normally been doing with our magnitude and phase plots from our open loop transfer characteristic. And that's what you'll see here, the phase plot without delay. Now, let's assume I do have some delay. So in terms of Laplace, what does that delay represent? It's an e to the minus st, where t is that delay time. So we now get a g prime, which is our transfer characteristic with that delay. Now, what we do is after we make this multiplication here, and then we go from s to j omega, what we'll see is that it has no impact on the magnitude, does not affect the magnitude, but the phase now is going to be delayed by a factor of omega t. So as we then plot that here, what you'll see, if this is the original phase with no time delay, here will be the phase, and you'll notice that slope a little bit different because of that delay. So what we're seeing just visually here, by adding that delay, what's going to happen is I have less and less phase margin associated with that. Okay, and also gain margin potentially as well, because notice now here is my 180 degrees, so my gain margin gets less as well. So you need to be very careful, because if you're playing with gain K and you ignore delay in your system, what you could be doing is not giving yourself enough gain or phase margin, because once that time delay gets really added in your physical system, i.e. you didn't model it, but then the physical system has it, what you might notice is that your system may go unstable, and that can be a source of many reasons why that can occur. So don't underestimate any time delays that you have in a system here. So I just wanted to bring this to your attention. Okay? So what we're going to do is work an example to kind of show you some of this. So let's find the range of gain K to yield stability of this open loop transfer characteristic in a unity feedback system with a 1 second time delay added in that system. So first we're going to plot the Bode plots here with a gain K equal to 1, and first with and without time delay. So remember, the magnitude plot, there's one and only one magnitude plot, because the time delay does not affect the magnitude. So that's why you'll only see one plot as shown here. And again, hopefully you're comfortable based on your S, minus 1 here, and then your pole here at 10, you could always extend that out, but you could come up with this quick approximations of the magnitude. And also the phase, first of all, here system, the graph here in black is the system with no time delay. So system, again, here has no time delay associated with it, and that's here in black. Now you can model the time delay just by itself right there, and then the total system will include the system without the time delay plus the time delay sort of added together, and that's what you'll see here as part of what we're calling the total system. Okay? And so what you'll see, definitely between the system and the total function, there is a change relative to the phase plot. And so here's what we'll look at. First, at omega equal 0.81 radians per second, that's where the phase is going to be minus 180 degrees. Okay, so here is roughly that 0.8. Okay, and that's what you'll see is that system. That system there is at minus 180 degrees. Again, for the total response, the total response with the delay. That's that point right there. So that's that point for minus 180 degrees. And at that point, going up to here, what you'll see is that we're at just about minus 20 dB. So that would be the gain margin associated with that, with the magnitude plot here. And so what we could do is we could increase the gain by a factor of 10 raised to the 20.39 over 20. So we could basically find out how much gain, 20.39 dB, equating that's a little over a factor of 10, so about 10 and a half is the gain we could basically increase for that system. To be within to have a stable system. Okay. Now, if we look at the frequency here, 3.16, that's way over here. 3.16 here. Okay, 3.16. That's where the original system phase response hits 180 degrees. Again, that's with no delay. And at that frequency point right here, again, the 3.16, 3.16, okay, you have about 40 dB right here, about minus 40 dB of gain. So your gain in that case could increase by that factor a little over 100, about 110. So what you'll see comparing these two systems here is with the time delay, I'm a factor of 10 less gain that I can have due to a 1 second delay. Now, you could always sweep the amount of delay and see that impact of gain as well. But again, let's say you ignored the time delay. You set a gain, oh, hey, I can go up to 110. I'll set it at 50, half of that. and then I can still have a healthy phase margin associated with that. But then when you implement the real system, all of a sudden it's going unstable, and you're like, wait, I even put in a factor of 2 to be safe, and it's still bad. And then you start lowering the gain maybe from 50 to 30 or 25, and well, gosh, now I'm down by a factor of 4 or 25% of what I originally had, and I'm still unstable. What's going on? And it must be the hardware. The hardware's bad. Well, if you model the time delay, you'll see, I can only have a gain of about 10 to be stable. So again, very, very important. As we go through our systems, we've sort of ignored this time delay, but if you do have that system, some sort of process lag that you didn't model, some transfer characteristic or something that you did not model, that gain impact is very, very significant. Okay? So something to look at as maybe you find something that you model in simulation, but then you get out in the lab and something's off a little. Maybe I want you to start thinking, maybe there's some time delay or some time lags I haven't modeled. Okay? So final topic here is we want to obtain the transfer functions experimentally. So first we're going to describe a process, but what I note here is that some experience in intuition in this field is going to be definitely helpful and useful for you. But nonetheless, I think it's an important process to go through. Got to start somewhere. So from the Bode plots, let's assume you've obtained these Bode plots, again, from a network analyzer or a spectrum analyzer or something, and then you want to sort of find out the transfer characteristics. So you'll start with those Bode plots, and you're going to estimate the zero-pole configurations of the system. You're going to look at the initial magnitude of slope to determine the system type, right? If it's a flat slope, again, type 0, minus 20 dB per decade, that's a type 1, minus 40 dB per decade, that's a type 2. So you're going to identify the system type. Then you're going to look at some of the phase excursions to determine the number of poles and zeros, right? Because as I have more and more poles, the phase is going to get more, add another, 45 per decade or et cetera, or the zeros would increase it. So as my phase either goes up or down or flattens out, I can determine, okay, maybe there's a pole or a zero, or if it goes up at 90, okay, maybe there's a 2 poles, et cetera. So that's sort of, we're going to start identifying that. Then we're going to see if we can identify if portions of the magnitude and phase curves represent obvious first or second order pole or zero frequency plots. Then we'll see if there's any peaking or depressions in the magnitude plot that might indicate an underdamped second order pole peak. So again, what we saw in that magnitude plot, right, that peak that goes up, that might be, again, an underdamped system with low damping. Or we didn't really talk about it, but if there's more of a depression, that would be a zero in that magnitude plot. Then finally, the next step is if any pole or zero response can be identified, we're going to start overlaying the appropriate, 20 dB or 40 dB plus or minus lines on the magnitude plot, or again, the phase plots as shown there, and try to estimate where those break frequencies are. That'll identify the poles and zeros. And then for second order poles or zeros, we're going to try to estimate the damping ratio and natural frequency from those standard curves that we've previously provided. And again, those are some of the second order Bode plot curves with the corrections added, where notice those contours were there as a function of damping ratio. Remember, smaller damping ratios had more of a sharp curve transition, especially in the phase response. Then we're going to form a transfer function of unity gain using the poles and zeros found, and then maybe obtain the frequency response of this transfer function, subtract it from the previous response to obtain a less complex frequency response, and then begin that process over to extract more poles and zeros until that response after you subtract the last one is more or less flat. And then that means you're pretty much done. So let's just go right into an example and show you at least an approach of how to do this. And what I'll say is it's going to be easier watching somebody do this and kind of sit back and say, yeah, I see what you're doing. I see what you're doing here. Yep, that looks good. But when you first get one of these yourself, trying to make these decisions by yourself without having somebody tell you what they are, that gets to be the challenge. So what do? You don't just take your pen and throw it down. You basically roll up your sleeves and you do many, many, many examples of this until you start getting that knack, that experience, that insight, okay? So here are our Bode plots, magnitude and phase, and so we'll start to make some observations here. So the first observation we'll make is that a natural frequency can be estimated from the peak frequency here at about 5 radians per second. So we notice this little peaking here at about 5 radians per second right down there. Okay, that peak from the initial slope looks like it goes up about 6.5 dB, and that would, again, from our previous charts, we can quickly identify a damping ratio of about 0.24. So we definitely know there's a second order transfer function of our general form as shown here. And so again, we know the natural frequency of 5, so we know omega n squared, and then we know our damping ratio, so we can basically estimate that second order transfer characteristic based on that initial sort of system right there, and we'll call that G1. So now what we're going to do is, now that we have G1, we're going to say here's a Bode plot of G1, and then we're going to subtract that from the original, and we're going to obtain the following Bode plot. Okay, so basically what we're doing is we're taking sort of the initial the initial transfer characteristic here, then we're going to come up with our G1 Bode plot, and then we're essentially going to subtract the two out. And then what we'll do is we'll see here next that a final pole is detected given the minus 20 dB per decade overlays that we're showing down here. We have these 20 dB per decade overlays as shown there. And what we'll see is that there's going to be essentially a break frequency of about 90 radians per second. Okay, right about there, about 90 radians per second. It's estimated, okay? So you might look at that and say, well, maybe that's 80, or maybe it's 95, or whatever. We're just trying to get close, okay? And some of this will be a little bit of trial and error, but, for our, for now, we'll just say it's 90, and what we're going to also do is trying to get these transfer functions with 0 dB gain at 0 frequency. So that's why we have 90 in the numerator as well. And so this is a first order pole, so we have now a second transfer function G2 to take care of that. And then so now what we'll do is we'll plot the G2 and then subtract it from the second Bode plot. So now what we have is the original transfer function. We've subtracted G1. Now we've subtracted G2. And now we're going to see what we have left. And we have this. That then gets the same plot is plotted on the next slide as shown here. And that resulting Bode plot, when I look at that, okay, that's going to kind of resemble a lag compensator. So I'm going to overlay that compensator on that plot. And then basically I'll see that we have break frequencies of about roughly 9 and roughly about 30 radians per second. So again, this black waveform is my lag compensator that I'm sort of kind of overlaying. Now clearly, I mean, the blue one has those sort of characteristics. It starts flat and it sort of ends flat, and it has this transition. So I'm just kind of overlaying a generic upper and lower breakpoints here. Again, I'm estimating these. They're going to be relatively close, but again, that's part of that trial and error and that gut intuition that you're going to have to develop for yourself. So here, my first breakpoint at 9, that's a pole. Why? Because that then transitions it down, so I put that in the denominator. I then have a higher breakpoint here at 30, which is a 0, because that takes the pole minus 20 dB per decade, adds plus 20 dB, and makes it now 0. So that's why I know that. And then again, if I look at the factor here, 0.3, I need that so that at 0 frequency, right, S is equal to 0, so 0.3 times 30 will be 9, and then 9 over 9 is 1. So I have unity gain, or 0 dB, for my transfer characteristics. So that's how I obtain the 0.3. Then, again, I subtract the Bode plot of G3 from the previous one. And what I notice here is now we essentially get a flat magnitude and phase characteristic, which indicates that we're done. Okay, so we now have these 3 transfer characteristics as shown below. So our overall transfer function is going to be our G1, our G2, and then our G3. characteristics. Now, the only thing we added here was 0.11. So where did the 0.11 come from? That's going to be obtained from our low frequency gain of minus 19 dB as shown here. So by looking at that point, we can then again move that up to say 0 dB. And so from that characteristic, we can calculate that that's going to be 0.11. So we have these three cascaded transfer functions. We can now kind of multiply them together and get a complete transfer function as shown here. So what we would say is, this is our transfer characteristic, G of S, our open loop transfer function that we had from experimenting with our system. Now we can build a closed loop controller for that, whether it's unity feedback gain or something else, to make this behave the way we want. Now, the actual transfer function, because I plotted this, I know what that transfer function is. Here was the actual transfer function. And if I look at it, a few observations was, okay, this second order system looks pretty reasonable, right? That looks pretty reasonable. This lag compensator G3, right? That's 30 and 9. So this was essentially our lag compensator. And notice what we have here. We have 20 and 7. So again, depending on where we said 30, well, maybe we should have gone, we should have gone to 20, and 9, we should have gone to 7. Maybe should have shifted it over a little bit. So again, reasonably close. And then finally, the last one here, we had a pole of 90 versus 70. So again, if we shifted that lag compensator over, it would make sense that we shift that other pole over as well. So again, overall, what I would then say is plot both of these transfer functions on the same plot over each other and then kind of compare the magnitude and phase. And certainly you'll see areas where they're not in agreement. But overall, I would say, probably pretty close. Okay? So I think that's at least showing you the approach here that you could take. And the best way to get good at this is to do many, many examples. You'll start to see trends and making your estimates and approximations much better. Okay, so this will actually conclude this module. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.